Hello there and welcome to Midnight Science. I'm so glad you found your way here tonight. Maybe you've had a long day, or maybe you just find peace in thinking about the cosmos before sleep finds you. Either way, you're exactly where you need to be. Tonight, we're leaving Earth behind. We're drifting outward, past the moon, past the planets, beyond our sun and the familiar stars of the Milky Way. We're traveling to the most distant galaxies in the universe, those ancient islands of light scattered across the vast, dark ocean of space. Some of what you'll hear tonight may stir your sense of wonder. Other facts might simply wash over you like gentle waves, soothing and soft. There's nothing you need to remember, nothing you need to hold on to. Just let the words carry you, slowly and gently toward rest. If this kind of cosmic peace brings you comfort, feel free to like and subscribe. It helps others find their way here too, one curious soul at a time. Also, I'd love to know where you're tuning in from and what time it is there. It's fascinating to see how these videos connect people from around the world. But for now, let your shoulders drop, let your breathing deepen, and let's begin this quiet journey through the distant universe. Some galaxies are so far away, their light has traveled for over 13 billion years. When you look at a distant galaxy through a telescope, you're not seeing it as it is now. You're seeing it as it was long ago. Light takes time to travel, and the farther away something is, the older the light we receive. Some of the most distant galaxies we've observed sent their light toward us over 13 billion years ago, when the universe itself was still young. That light has been traveling through expanding space all this time, carrying a message from an era before Earth existed, before our sun was born, before most of the stars we see had even formed. These galaxies are like fossils made of light, frozen images from the childhood of the cosmos. We cannot know what they look like now. They may have merged with others, faded, or transformed entirely, but their ancient glow still reaches us, a whisper from the dawn of time. The farthest galaxies appear red due to cosmic expansion. Distance doesn't just delay light, it changes it. As the universe expands, space itself stretches, and light traveling through that space stretches too. This stretching shifts light toward longer wavelengths, toward the red end of the spectrum. The effect is called redshift, and it's how astronomers measure distance. The more redshifted a galaxy's light, the farther away it is, and the faster it's moving away from us. Some of the most distant galaxies appear so deeply red that they're almost invisible in ordinary telescopes. Only infrared instruments can see them clearly. What began as ultraviolet or blue light has been pulled across the spectrum by billions of years of expansion. These galaxies glow softly in wavelengths our eyes were never meant to see, painted red by the slow, patient breathing of the universe. Galaxies form in clusters held together by invisible gravity. Galaxies don't drift alone through space. Most live in neighborhoods, bound together by gravity into clusters. Some clusters contain dozens of galaxies, others hold thousands. These clusters span millions of light years and contain more mass than 1 trillion suns. But most of that mass isn't in stars or gas. It's dark matter, an invisible substance that doesn't emit or absorb light. We can't see it directly, but we know it's there because of how galaxies move and how light bends around these clusters. Dark matter acts like invisible scaffolding, holding clusters together and shaping how galaxies interact. In these cosmic cities, Galaxies drift slowly around one another, sometimes colliding, sometimes passing by like ships in the night. And all of it, every motion, every pull, is guided by gravity's quiet hand. Some distant galaxies are colliding in slow motion. Out in the distant universe, galaxies meet. When two galaxies pass close enough, their gravity pulls at each other, warping their shapes and stirring up waves of star formation. These collisions happen over hundreds of millions of years, too slow for any human to witness in a lifetime. But through telescopes, we can see galaxies frozen in the act, stretched into arcs, rings, and tidal tails. Stars themselves rarely collide because the space between them is so vast. Instead, they pass through one another like two swarms of fireflies merging in the dark. Gas clouds compress, triggering bursts of new stars. Dust lanes twist and glow. Eventually, the two galaxies may merge completely, forming a single larger galaxy with a new shape and a new future. These distant collisions remind us that even on cosmic scales, nothing stays the same. Everything moves, everything changes, everything dances. The Hubble Deep Field revealed thousands of galaxies in a tiny patch of sky. In 1995, astronomers pointed the Hubble Space Telescope at what seemed like an empty patch of sky, no bigger than a grain of sand held at arm's length. They left the camera open for several days, collecting every faint photon they could. What emerged was astonishing. That tiny dark patch wasn't empty at all. It was filled with thousands of galaxies, each one a vast collection of stars stretching back billions of years into the past. Some were spirals, others were elliptical or irregular. Many were so faint and distant that they had never been seen before. This image, called the Hubble Deep Field, changed how we see the universe. It revealed that no matter where we look, the cosmos is full. Not empty, not barren, just filled with islands of light drifting quietly through the dark. Every galaxy contains hundreds of billions of stars. A galaxy isn't just a smudge of light in the sky. It's a vast system, an entire world of stars. Our own Milky Way contains between 200 and 400 billion stars. And it's not unusual. Many large galaxies hold similar numbers. Some, like the giant elliptical galaxies at the centers of clusters, contain trillions. Each of those stars is a sun, many with their own planets, moons, and perhaps life. The scale is almost impossible to grasp. If you tried to count the stars in a single large galaxy, one per second, it would take you thousands of years. And there are hundreds of billions of galaxies in the observable universe, each one a city of suns, each one humming with light, gravity, and motion. When you look at a distant galaxy, you're not just seeing one thing. You're seeing an entire civilization of stars, living and dying across unimaginable time. Some galaxies stopped forming stars billions of years ago. Not all galaxies are still alive with new stars. Some, especially the massive elliptical galaxies, exhausted their star-forming gas long ago. These galaxies are filled with old red stars, the survivors of ancient generations. No new blue stars are born there. No bright nebulae glow with fresh creation. They're quiet, settled, and fading. Over time, their stars will age and cool, and the galaxies will grow dimmer. Astronomers call these red and dead galaxies. They reached their peak billions of years ago and have been slowly declining ever since. But they're not lifeless. Inside them, stars still orbit, black holes still lurk, and planets may still circle ancient suns. They're just finished growing. Like old forests where the trees no longer sprout, but still stand tall. These galaxies rest in the gentle twilight of cosmic age. Spiral galaxies have arms made of stars and gas. When you picture a galaxy, you might imagine a spiral, arms curving gracefully outward from a bright center. Spiral galaxies, like our Milky Way, are among the most beautiful structures in the universe. Their arms aren't solid. They're regions where stars, gas, and dust gather more densely, like traffic slowing on a highway. As the galaxy rotates, these density waves move through the disk, compressing gas and triggering star formation. The bright blue stars that form there don't live long, so the arms constantly refresh with new generations. The stars themselves don't stay in the arms. They drift in and out, but the pattern persists, a slow rotating wave of light. In the quiet dark, spiral galaxies spin like pinwheels, patient and eternal, their arms tracing paths through space that have existed for billions of years. Elliptical galaxies are smooth and featureless. Unlike spirals, elliptical galaxies have no arms, no disk, no clear structure. They're smooth, rounded, and filled with older stars that orbit in random directions. Some are nearly spherical, others are stretched into elongated ovals. They range in size from small dwarfs to massive giants that dominate galaxy clusters. Elliptical galaxies often form through mergers. When two spirals collide and merge, their organized rotation is disrupted, and what remains is a featureless ellipsoid. These galaxies are quieter than spirals. They contain little gas or dust, so they rarely form new stars. They glow with a soft, steady light, the combined glow of trillions of aging suns. In their stillness, they hold a kind of cosmic peace, a galaxy that has settled into its final form and now simply exists, glowing gently in the dark. Irregular galaxies have chaotic, asymmetric shapes. Not all galaxies fit into neat categories. Some are irregular, with no clear structure at all. They're lumpy, chaotic, and often filled with active star formation. These galaxies may have been disturbed by collisions, tidal forces, or close encounters with larger neighbors. Others are simply young, still in the process of forming, and haven't yet settled into a stable shape. The small and large Magellanic Clouds, satellite galaxies of the Milky Way, are examples of irregular galaxies. They're visible from the southern hemisphere as faint cloudy patches in the night sky. Despite their disorder, irregular galaxies are vibrant and full of life. Gas clouds glow with new stars. Dust lanes twist and swirl. In their asymmetry, they remind us that not everything in the universe follows a pattern. Some things are beautifully, brilliantly messy. The most massive galaxies live at the centers of clusters. In the heart of nearly every large galaxy cluster sits a giant, a massive elliptical galaxy that has grown by consuming its neighbors. These brightest cluster galaxies, or BCGs, can be 10 times more massive than the Milky Way. They're surrounded by halos of hot gas and sprinkled with globular clusters, dense balls of ancient stars. BCGs grow slowly over time, pulling in smaller galaxies through gravity. Each merger adds mass, stars, and dark matter. Some BCGs have multiple cores, the remnants of galaxies they've recently absorbed. Despite their size, they're not violent. They sit calmly at the bottom of the cluster's gravitational well, slowly gathering mass like cosmic spiders at the center of a web. They are the elder giants of the universe, patient, ancient, and impossibly vast. Quasars are the brilliant hearts of distant galaxies in the early universe. Some galaxies burned with incredible brightness. At their centers sat supermassive black holes, feeding on vast amounts of gas and dust. As matter spiraled inward, it heated up and glowed with intense radiation, sometimes outshining the entire galaxy around it. These objects are called quasars, and they're among the most luminous things in the universe. We see them only at great distances because they existed billions of years ago, when galaxies were younger and more chaotic. Today, most quasars have faded. Their black holes ran out of fuel, and the galaxies settled into quieter lives. But in the deep past, quasars blaze like beacons, lighting up the young cosmos. Their light has traveled for eons to reach us, carrying stories of a universe far more violent and alive than the one we see today. Some galaxies contain supermassive black holes at their cores. At the center of nearly every large galaxy, including our own, lies a supermassive black hole. These aren't the remnants of dead stars. They're something else entirely. Black holes millions or even billions of times the mass of the Sun. We don't fully understand how they formed, but they seem to grow alongside their galaxies, influencing star formation and shaping the structure around them. The black hole at the center of the Milky Way, called Sagittarius A, is about 4 million solar masses. Others are far larger. The black hole in the galaxy M87 is over 6 billion solar masses, so massive that its shadow was photographed by the Event Horizon telescope. These black holes don't pull everything in. Most of the time they sit quietly, surrounded by orbiting stars. But when they feed, they can unleash jets of energy that stretch for millions of light years. Silent, invisible, and immensely powerful, they are the hidden anchors of galaxies. Galaxies move through space at hundreds of kilometers per second. Nothing in the universe is still. Galaxies drift through space pulled by gravity, pushed by cosmic expansion, and swept along by invisible currents. Our Milky Way is moving toward the Andromeda Galaxy at about 110 kilometers per second. Both are part of the local group, which is falling toward the Virgo cluster. And the Virgo cluster itself is being pulled toward an even larger structure called the Great Attractor. These motions are slow on human scales, but vast across cosmic time. Over millions of years, galaxies shift, merge, and scatter. The universe is not a static painting. It's a flowing river of light and matter, always moving, always changing. Even as you rest, the ground beneath you is hurtling through space, part of a galaxy traveling through the dark. The cosmic web connects galaxies across the universe. If you could zoom out far enough to see the entire observable universe, you'd notice a pattern. Galaxies aren't scattered randomly. They cluster along vast filaments like beads on a cosmic string. Between these filaments lie enormous voids, regions almost empty of galaxies. This structure is called the cosmic web, and is the largest pattern in the universe. The filaments are shaped by dark matter, which acts like invisible threads pulling galaxies together. Where filaments intersect, superclusters form, enormous knots of galaxies spanning hundreds of millions of light years. The cosmic web formed over billions of years, guided by gravity and the initial fluctuations left over from the Big Bang. It's a network so vast and intricate that it resembles neurons in a brain or roots in soil. The universe, it seems, grows structure the way life does, branching, connecting, weaving itself into form. Some galaxies are gravitationally lensed by others. Sometimes, light from a distant galaxy passes close to a massive object, like a galaxy cluster, on its way to us. The cluster's gravity bends the light, acting like a giant lens. This effect, called gravitational lensing, can magnify, distort, or even multiply the image of the background galaxy. We see arcs, rings, or multiple copies of the same object. Gravitational lensing allows us to study galaxies that would otherwise be too faint or distant to observe. It also helps astronomers map dark matter, since the bending of light reveals where mass is concentrated. Some of the most beautiful images in astronomy come from lensing. Glowing arcs and rings wrapped around massive clusters. It's a reminder that space isn't flat. It curves, bends and warps, and light, patient and persistent, follows every curve. The first galaxies formed just a few 100 million years after the Big Bang. The universe began in darkness. For the first few 100 million years, there were no stars, no galaxies, just clouds of hydrogen and helium drifting through expanding space. But slowly, gravity began to pull those clouds together. In the densest regions, the first stars ignited, massive, hot and short-lived. They clustered into small chaotic systems, the seeds of the first galaxies. These early galaxies were nothing like the grand spirals we see today. They were small, irregular, and filled with intense star formation. Over time, they merged, grew, and evolved into the larger galaxies we observe now. Studying the first galaxies is like looking at baby pictures of the universe. They show us how structure began, how light first broke through the cosmic fog, and how the universe transformed from darkness into the luminous web we see today. Some galaxies shine primarily in infrared light. Not all galaxies are bright invisible light. Some are shrouded in dust, which absorbs and scatters shorter wavelengths like blue and ultraviolet, but allows longer infrared wavelengths to pass through. These dusty galaxies are often sites of intense star formation, where gas collapses into stars faster than in normal galaxies. The dust, heated by young stars, glows brightly in infrared. To study these galaxies, astronomers use infrared telescopes like the James Webb Space Telescope. What looks like an empty patch of sky in visible light can reveal dozens of hidden galaxies in infrared. These galaxies remind us that the universe is full of things we can't see with our eyes alone. Some of the most active, vibrant galaxies in the cosmos glow not in visible light, but in wavelengths just beyond our perception. Dwarf galaxies orbit larger ones like moons. Just as planets have moons, galaxies have satellites. These dwarf galaxies are much smaller, often containing only a few billion stars or less. They orbit larger galaxies, held in place by gravity. The Milky Way has dozens of known satellite galaxies, including the large and small Magellanic Clouds. These dwarfs are ancient, some of the oldest galaxies in the universe. Over time, many will be absorbed by their larger hosts, their stars scattered into the bigger galaxy's halo. Others may survive for billions of years, quietly orbiting like faithful companions. Dwarf galaxies are windows into the early universe. Because they're small and simple, they haven't evolved as much as larger galaxies. Studying them helps us understand what galaxies were like long ago, when the universe was young and everything was still taking shape. Some galaxies produce gamma-ray bursts. In rare cases, distant galaxies host one of the most violent events in the universe, a gamma ray burst. These bursts are short-lived, lasting from milliseconds to minutes, but during that time, they release more energy than the sun will emit in its entire lifetime. Gamma ray bursts are thought to come from collapsing massive stars or merging neutron stars. The burst itself is a narrow beam of radiation, so we only see it if the beam happens to point toward Earth. When we do, it's blinding. Even from billions of light years away, gamma ray bursts can be detected by satellites. They're fleeting, violent, and astonishingly powerful. For a brief moment, a single exploding star in a distant galaxy can outshine everything else in the sky. Then, just as quickly, the light fades, and the galaxy returns to silence. Galaxy mergers trigger waves of new star formation. When two galaxies collide, their gas clouds compress, and the pressure triggers bursts of new star formation. These starburst galaxies can form stars hundreds of times faster than the Milky Way. The stars that form are often massive and blue, burning hot and bright, but dying quickly. The galaxies glow intensely, filled with young stars, glowing nebulae, and supernova remnants. Over time, the starburst fades. The gas runs out, the massive stars die, and the galaxy settles down. But during the burst, the galaxy is alive with light and energy, a cosmic fireworks display that can last for millions of years. Galaxy mergers reshape the universe, building larger structures and redistributing matter. They're not gentle, but they're creative. Out of chaos comes new stars, new planets, and perhaps new chances for life. Some galaxies have jets of plasma shooting from their cores. At the centers of certain galaxies, supermassive black holes don't just pull matter in, they also push it out. Powerful magnetic fields accelerate particles to nearly the speed of light, launching narrow jets of plasma that stretch for millions of light years. These jets are visible in radio wavelengths, glowing like cosmic searchlights. They plow through the space around the galaxy, creating shock waves and heating the surrounding gas. Galaxies with these jets are called active galactic nuclei, or AGN. They're among the most energetic objects in the universe. The jets themselves don't contain much mass, but they carry enormous amounts of energy. Over time, they can affect the galaxy's ability to form stars, blowing away gas and regulating growth. In the deep cosmos, these jets are like exhaust from the engines of the universe, silent, invisible, and immensely powerful. The Andromeda Galaxy is on a collision course with the Milky Way. Our nearest large galactic neighbor, Andromeda, is moving toward us. In about 4 billion years, the two galaxies will collide. It won't be a sudden crash. The process will take hundreds of millions of years. Stars will pass by one another without touching, but the shapes of both galaxies will be warped and distorted. Gas clouds will collide, triggering bursts of star formation. Eventually, the two galaxies will merge into a single, larger elliptical galaxy. Some have nicknamed this future galaxy Milkomeda or Milkdromeda. It's a distant fate, and life on Earth, if it still exists, will have long since faced other challenges, like the aging of the sun. But the collision is inevitable. The two galaxies are already close enough that their outer halos are touching. Slowly, gently, they drift toward one another, drawn by gravity across the dark. Some galaxies appear to have no dark matter. Dark matter is thought to be essential for galaxy formation. It provides the gravitational scaffolding that holds galaxies together. But recently, astronomers discovered galaxies that seem to have little or no dark matter at all. These ultra-diffuse galaxies move as if they contain only the visible matter we can see, stars and gas. How this is possible is still a mystery. Some think the dark matter was stripped away during close encounters with larger galaxies. Others wonder if these galaxies formed in unusual ways. A few scientists even question whether dark matter behaves the way we think it does. These anomalies remind us that the universe still holds surprises. Just when we think we understand the rules, we find something that doesn't fit. And in those exceptions, new questions arise. Galaxies can be billions of light years away and still visible. The observable universe is about 93 billion light years across, and we can see galaxies from nearly edge to edge. Some of the most distant galaxies ever observed are over 13 billion light years away. Their light has been traveling toward us since the universe was less than 1 billion years old. By the time that light reaches our telescopes, it's been stretched, redshifted, and faded almost to invisibility, but it's still there. With sensitive instruments, we can capture it, analyze it, and learn about galaxies that existed in the first chapter of cosmic history. The fact that we can see so far is astonishing. It means we can look not just across space, but across time. Every distant galaxy is a glimpse into the past, a window into a universe younger, smaller, and stranger than the one we know today. Some galaxies rotate backward. Most galaxies rotate in one direction, their stars and gas orbiting the center in a coordinated flow. But a few galaxies rotate in two directions at once. Their inner regions spin one way, while their outer regions spin the opposite way. These counter-rotating galaxies likely formed through mergers, when one galaxy absorbed another that was spinning differently. The result is a galaxy with a split personality, two systems overlaid on each other, each moving to its own rhythm. It's a reminder that galaxies have histories, stories, written in their motion, structure, and chemistry. Every twist, every tilt, every oddity tells us something about what that galaxy has experienced. And in the case of counter-rotating galaxies, the story is one of collision, disruption, and transformation. Dark matter makes up most of a galaxy's mass. When you look at a galaxy, you're seeing only a fraction of what's there. The stars, gas, and dust, everything that glows, accounts for less than 20% of the galaxy's total mass. The rest is dark matter, invisible and mysterious. We don't know what dark matter is made of. It doesn't emit, absorb, or reflect light. But we know it's there because galaxies wouldn't hold together without it. Stars in the outer regions of galaxies move faster than they should, based on visible matter alone. The only explanation is that they're being pulled by something we can't see. Dark matter forms halos around galaxies, vast invisible spheres that extend far beyond the visible edge. These halos shape how galaxies move, interact, and evolve. In a very real sense, galaxies are icebergs. What we see is just the tip. The rest lies hidden, quiet, and essential. Some galaxies shine in X-rays. Most of the light from galaxies comes from stars, which shine in visible and infrared wavelengths. But some galaxies also emit X-rays, high-energy radiation that comes from extremely hot or energetic processes. X-rays can be produced by gas heated to millions of degrees, often found in galaxy clusters. They can also come from black holes actively feeding on matter, or from neutron stars and supernova remnants. X-ray observations reveal a different side of galaxies, the violent, energetic side that remains hidden in visible light. With X-ray telescopes like Chandra, astronomers can map hot gas, track the activity of black holes, and study the aftermath of stellar explosions. The universe, it turns out, glows in many colors. Some we can see, others require special eyes. Galaxies evolve over billions of years. A galaxy is not a fixed object. It changes over time, sometimes slowly, sometimes dramatically. In the early universe, galaxies were smaller, more irregular, and filled with intense star formation. Over billions of years, they merged, grew, and settled into more stable shapes. Spirals formed disks. Ellipticals grew through collisions. Star formation slowed as gas was consumed or blown away. Today's galaxies are calmer, more organized. But they're still evolving. Mergers still happen. Stars still form and die. Black holes still feed. And billions of years from now, galaxies will look different again. The universe is not a snapshot. It's a film, a slow unfolding story that spans eons. Every galaxy is a character in that story, shaped by time, gravity, and chance. Some distant galaxies look like tadpoles or jellyfish. Not all galaxies are neat and symmetrical. Some have strange, distorted shapes that tell stories of recent upheaval. Tadpole galaxies have long tails of stars and gas stretching behind them, created by tidal forces during close encounters. Jellyfish galaxies have streams of material dripping away, stripped off by the hot gas in galaxy clusters. These shapes are temporary, snapshots of galaxies caught in the act of transformation. Over time, the tails and streams will fade, and the galaxies will settle into new forms. But for now, they drift through space with their strange silhouettes, reminders that galaxies are not static sculptures. They're living, changing, responding to the forces around them. And in their distorted shapes, we glimpse the dynamic, restless nature of the cosmos. The Milky Way contains over 200 billion stars. Our home galaxy, the Milky Way, is vast. It stretches about 100,000 light-years across and contains an estimated 200 to 400 billion stars. That's more stars than there are people who have ever lived on Earth. Many of those stars have planets. Some of those planets might have life. We live on a small world orbiting an average star in the outer suburbs of this galaxy, about 2/3 of the way from the center to the edge. The Milky Way is a spiral galaxy with graceful arms curving outward from a bright central bulge. It rotates slowly, taking about 230 million years to complete one full turn. Everything in it, the sun, the planets, the dust and gas, moves together in a cosmic dance. When you look up at the night sky and see the faint band of the Milky Way stretching overhead, you're seeing the combined light of billions of stars, our neighbors, our companions in the dark. Some galaxies are so old they formed when the universe was young. The oldest galaxies we've observed date back to just a few 100 million years after the Big Bang. These galaxies are small, faint, and primitive, but they're also incredibly important. They represent the first generation of galactic structures, the building blocks that would later merge and grow into the galaxies we see today. Studying these ancient galaxies helps us understand how the universe evolved from a smooth, featureless state to the complex web of structures we see now. It also raises questions. Some of these early galaxies seem more mature than they should be, with organized structures and populations of stars that suggest rapid evolution. How did they grow so quickly? What processes were at work in the early universe? the answers are still unfolding, written in the faint light of galaxies born when the cosmos was still learning how to build itself. Galaxies can be caught in the act of transformation. Telescopes don't just show us what galaxies look like, they show us what they're doing. Some galaxies are caught mid-merger, their spiral arms stretched and distorted. Others are in the middle of a starburst, their cores glowing with the light of 1 million newborn stars. Still others are fading, their gas exhausted, their star formation winding down. These snapshots give us clues about how galaxies change. By observing galaxies at different stages, we can piece together the story of galactic evolution, like watching a time-lapse made of individual frames. Every galaxy we see is a moment in a much longer process, and in those frozen moments, we glimpse the forces that shape the universe: gravity, gas, stars, and time. Some galaxies have rings instead of arms. Not all spiral galaxies have arms. Some have rings, circular structures of stars and gas that orbit the galactic center. These ring galaxies can form when a smaller galaxy passes directly through the center of a larger one, creating a ripple effect like a stone dropped in water. The collision sends a wave of density outward, compressing gas and triggering star formation in a ring. Over time, the ring expands and fades. Ring galaxies are rare and beautiful, glowing halos of blue stars surrounding a quieter core. They're temporary structures, snapshots of a moment when two galaxies crossed paths. In time, the ring will dissolve and the galaxy will settle into a new shape. But for now, it wears its collision like a cosmic scar, a memory written in light. Ultra-diffuse galaxies are nearly invisible. Some galaxies are so faint they're almost impossible to see. Ultra-diffuse galaxies, or UDGs, are spread out over vast regions of space, making their light incredibly dim. They can be as large as the Milky Way, but contain far fewer stars, sometimes just 1% as many. These ghostly galaxies were discovered only recently because they're so hard to detect. They blend into the background of space, their faint glow easily lost among brighter objects. Scientists aren't sure how they formed. Some may be failed galaxies, systems that never gathered enough gas to form many stars. Others might have been stripped of their gas by larger neighbors. Whatever their origin, ultra-diffuse galaxies remind us that the universe contains structures at the edge of visibility, things that exist in the space between bright and dark, present but barely perceptible. Some galaxies produce winds that blow for millions of years. At the centers of active galaxies, powerful winds blow outward from the core, driven by energy from supermassive black holes or intense star formation. These galactic winds can reach speeds of thousands of kilometers per second, carrying gas, dust, and even entire star systems with them. The winds blow for millions of years, reshaping the galaxy from within. They can halt star formation by removing the raw materials needed to make new stars. They can also enrich the intergalactic medium with heavy elements, spreading the products of stellar fusion across space. These winds are invisible in most wavelengths, but astronomers can detect them through their effects on surrounding gas. They're like the breath of galaxies, exhaling matter and energy into the void, shaping not just themselves, but the space around them. Galaxies can contain globular clusters older than the galaxy itself. Globular clusters are dense, spherical collections of stars that orbit galaxies like satellites. Some contain hundreds of thousands of stars packed into a region, just a few dozen light years across. Many globular clusters are incredibly old, dating back more than 12 billion years. In some cases, they're older than the galaxy they orbit. How is this possible? These clusters likely formed in smaller, earlier galaxies that were later absorbed by larger ones. The clusters survived the merger intact, becoming part of a new galactic system. They're like ancient relics, carried forward through time and space, witnesses to the birth of the first stars. Looking at a globular cluster is like looking at a fossil, a preserved piece of the early universe, still glowing softly in the present. The light from some galaxies has been traveling since before Earth existed. When we observe a galaxy 5 billion light-years away, we're seeing light that left that galaxy 5 billion years ago. Earth is only about 4.5 billion years old. That means the light we're seeing began its journey before our planet even formed, before the sun ignited, before the solar system coalesced from a cloud of gas and dust. That light traveled through empty space, through expanding universe, across unimaginable distances, and finally arrived at our telescopes tonight. It carries information about a galaxy that may no longer exist in the form we see. It's a message from a time when the universe was younger, wilder, and still in the early stages of building the structures we see today. Every distant galaxy is a time machine, and every photon is a traveler from the past. Some galaxies are shaped like cigars or footballs. Most galaxies are either spirals or ellipticals, but a few have unusual shapes. Some elliptical galaxies are stretched into elongated forms, like cigars or footballs. These galaxies likely formed through mergers where the collision happened at just the right angle to stretch the resulting galaxy along one axis. They rotate slowly, their stars moving in complex, chaotic orbits. Viewed from different angles, they can look very different, appearing round from one direction and elongated from another. These cigar-shaped galaxies are reminders that galactic structure is shaped by history. Every bump, bulge, and stretch tells a story of past interactions, forces applied over millions of years, and the slow reshaping of matter under gravity's patient hand. Galaxies have halos of hot gas that extend beyond the visible edge. Surrounding most galaxies is a vast halo of hot, diffuse gas, often heated to millions of degrees. This gas extends far beyond the visible stars, sometimes 10 times the radius of the galaxy itself. It's detected through X-ray observations, glowing faintly in wavelengths invisible to the naked eye. This hot halo is part of the galaxy's ecosystem. It's fed by stellar winds, supernova explosions, and gas falling in from intergalactic space. Some of it cools and falls back into the galaxy, fueling new star formation. Some is blown away by galactic winds. The halo is a reservoir, a buffer, and a history book, holding traces of past events written in temperature and composition. Most of a galaxy's story is told not in its star, but in the invisible gas surrounding them. Some galaxies are fossils from the early universe. A few rare galaxies have remained almost unchanged since the early universe. These relic galaxies are compact, dense, and filled with old stars. They formed quickly, built most of their stars in a short burst billions of years ago, and then stopped. Unlike most galaxies, they didn't merge with others or grow over time. They've been drifting through space in isolation, untouched and unaltered. Studying these galaxies is like finding a living fossil, a glimpse of what galaxies looked like when the universe was young, They're rare because most galaxies have had eventful lives, merging, transforming, evolving. But these few quiet survivors offer a window into the past, frozen in time, holding secrets about how galaxies first formed and what they looked like in their infancy. Galaxies are recycling factories for matter. Nothing in a galaxy is wasted. Stars form from clouds of gas and dust. They live, fuse elements in their cores, and eventually die. When they die, they return their material to space, either gently through stellar winds or violently in supernova explosions. That material, now enriched with heavier elements, mixes back into the interstellar medium. New clouds form, new stars ignite. The cycle continues. Over billions of years, the same atoms are used and reused, cycling through generations of stars. The carbon in your body, the oxygen you breathe, the iron in your blood, all were forged in stars, released into space, and gathered into new systems. Galaxies are not just collections of stars. They're cosmic recycling centers, endlessly transforming matter from one form to another. Some galaxies have bars of stars across their centers. Many spiral galaxies, including our own Milky Way, have a bar-shaped structure running through their center. These galactic bars are made of stars, gas, and dust, and they rotate more slowly than the spiral arms. Bars play an important role in galactic evolution. They funnel gas from the outer disk toward the center, feeding the central black hole and triggering star formation in the core. Bars can also stabilize spiral arms, helping maintain the galaxy's structure. Not all spirals have bars, and some develop them over time through gravitational instabilities. Bars can also disappear if the galaxy undergoes a major merger. In the quiet rotation of a barred spiral, we see how structure and flow work together, guiding matter inward and shaping the galaxy from within. The universe contains more galaxies than grains of sand on Earth. It's hard to grasp the scale, but estimates suggest there are at least 100 billion galaxies in the observable universe, possibly as many as 200 billion or more. That's more than the number of grains of sand on all the beaches and deserts on Earth. Each galaxy contains billions or trillions of stars. Each star may have planets. The numbers multiply into scales that lose all meaning, becoming just abstract figures. But the point remains, the universe is vast beyond comprehension. Every tiny patch of sky, no matter how empty it seems, is filled with distant galaxies. Every direction you look stretches back billions of years and billions of light years. And in all that vastness, we occupy one small blue world, looking out, wondering, trying to understand. Some galaxies have tidal tails stretching millions of light years when two galaxies pass close to each other. Their gravitational pull can stretch stars and gas into long streams called tidal tails. These tails can extend for millions of light years, trailing behind the galaxies like ribbons. Some tidal tails curve gracefully through space. Others twist and loop back on themselves. Over time, the stars in these tails may fall back into one of the galaxies, or they may drift away entirely, becoming part of the intergalactic medium. Tidal tails are beautiful and haunting, evidence of past encounters written in the motion of stars. Their temporary structures, visible for only a few 100 million years before they fade. But while they last, they're among the most striking features in the cosmos, delicate threads of light stretching across the dark. Galaxies form stars in bursts and lulls. Star formation in galaxies isn't steady. It happens in waves, bursts of activity followed by quiet periods. During a burst, gas clouds collapse rapidly, forming thousands or millions of new stars in a short time. These bursts can be triggered by galaxy mergers, interactions with neighbors, or the compression of gas by spiral density waves. After a burst, the available gas is depleted or blown away by stellar winds and supernovae. The galaxy enters a lull, a period of reduced star formation. Over time, gas accumulates again, either from the galaxy's own reserves or from intergalactic space, and the cycle begins anew. This rhythm of burst and lull shapes the history of galaxies, determining when stars form, how quickly they evolve, and how the galaxy changes over time. Some galaxies glow with the light of dead stars. In older galaxies, especially massive ellipticals, most of the light comes not from young, bright stars, but from older, cooler ones. Red giants, white dwarfs, and aging main sequence stars dominate the population. These stars don't burn as brightly as young blue stars, so the galaxy has a softer, redder glow. There's a melancholy beauty to these galaxies. They're past their prime, no longer forming new stars, just gradually fading as their existing stars age and cool. But they're still luminous, still beautiful. They remind us that even in decline, there's grace. Even in old age, light persists. These galaxies will shine for billions more years, growing dimmer year by year, but never quite going dark. The smallest galaxies contain only a few thousand stars. At the other end of the scale, from giant ellipticals, are dwarf galaxies so small they barely qualify as galaxies at all. Some contain only a few thousand stars, far fewer than a large globular cluster. These ultra-faint dwarf galaxies are incredibly hard to detect. They're so dim that they're often found only when they pass in front of more distant objects or through careful surveys of nearby space. Despite their size, they're important. They may be the most common type of galaxy in the universe, vastly outnumbering larger galaxies, and they're old, likely among the first galaxies to form. Studying them helps us understand how galaxies began, how structure emerged from the smooth early universe, and how the smallest systems survive in a cosmos dominated by giants. Some galaxies shine with light from active supermassive black holes. In the centers of active galaxies, supermassive black holes feed on surrounding gas, heating it to millions of degrees. This process releases enormous amounts of energy, sometimes outshining all the stars in the galaxy combined. These active galactic nuclei, or AGN, come in different forms. Quasars are the brightest. Seyfert galaxies are less luminous, but still active. Blazars have jets pointed directly at us, making them flicker and flare. All are powered by the same process, matter falling into a black hole, releasing energy as it spirals inward. AGN are more common in the distant universe, suggesting that black holes were more actively feeding when the universe was younger. Today, most supermassive black holes are quiet, dormant, but in the past, they blazed, lighting up the cosmos with their ferocious hunger. Galaxies can be lensed into Einstein rings. When a massive galaxy or galaxy cluster lies directly between us and a more distant galaxy, the foreground object's gravity can bend the light from the background galaxy into a perfect ring. These Einstein rings are rare and beautiful, glowing circles of distorted light that seem to wrap around the lensing galaxy. They're named after Albert Einstein, who predicted that gravity could bend light. Einstein rings are not just beautiful, they're useful. By studying the distortion, astronomers can measure the mass of the lensing object, including its dark matter. They can also magnify and study the background galaxy in detail. In these perfect circles, we see both beauty and science, art and information, woven together by the curvature of space-time. Some galaxies have been observed forming stars since the Big Bang. A few galaxies have been continuously forming stars for most of cosmic history. They started forming stars shortly after the Big Bang and haven't stopped. These galaxies have maintained a steady supply of gas, either from their own reserves or by pulling in material from their surroundings. They're rare because most galaxies go through periods of quiescence, times when star formation slows or stops. But these persistent star formers remind us that not all galaxies follow the same path. Some burn bright and fast. Others glow steadily for billions of years. Each galaxy has its own story, its own rhythm, its own way of moving through time. And in the diversity of galaxies, we see the diversity of cosmic history itself. The cosmic microwave background reveals the seeds of galaxies long before galaxies existed. The universe was filled with tiny fluctuations, slight differences in density and temperature. These fluctuations were imprinted in the cosmic microwave background, the faint glow left over from the Big Bang. Over billions of years, gravity amplified these tiny variations. Dense regions pulled in more matter. Underdense regions became voids. Eventually, the overdense regions collapsed into the first stars and galaxies. By studying the cosmic microwave background, astronomers can see the seeds of structure, the first hints of where galaxies would eventually form. It's like looking at a map of the future written in the past. Those tiny ripples, barely visible in the early universe, grew into the vast cosmic web we see today. Some galaxies are home to millions of black holes. Every massive star that dies in a supernova leaves behind a remnant, either a neutron star or a black hole. Over billions of years, galaxies accumulate these stellar corpses. A large galaxy like the Milky Way may contain millions of stellar mass black holes, scattered throughout the disk and halo. Most are invisible, silent, and alone. They don't emit light, and they're not actively feeding, but they're there, drifting through space, remnants of stars that collapsed long ago. Occasionally, two black holes meet and merge, releasing gravitational waves that ripple across the universe. These mergers are rare, but they happen, and when they do, they send out a signal we can detect even from billions of light years away. In the quiet darkness of galaxies, black holes wait, unseen and eternal. Galaxies can be studied through their radio emissions. Many galaxies emit radio waves produced by energetic processes like supernova remnants, pulsars, and active galactic nuclei. Radio telescopes can detect these emissions, revealing structures and processes invisible in visible light. Radio observations show us the magnetic fields threading through galaxies, the jets shooting from black holes, and the distribution of cold hydrogen gas. They also help us study galaxies hidden behind dust or located at great distances where visible light has been stretched into infrared. Radio astronomy has opened a new window on the universe, showing us that galaxies are not just collections of stars, but complex, dynamic systems filled with fields, flows, and forces we're only beginning to understand. Some galaxies have multiple supermassive black holes. When two galaxies merge, their central black holes eventually sink toward the center of the new galaxy. For a time, both black holes orbit each other, a binary system at the heart of the merged galaxy. These dual black holes are rare but have been observed. Eventually, they'll merge, releasing a burst of gravitational waves and forming a single, more massive black hole. But the merger can take millions of years. During that time, the galaxy has two centers of gravity, two sources of energy, two potential AGN. The dynamics are complex, chaotic, and fascinating. Studying these systems helps us understand how supermassive black holes grow and how galaxy mergers reshape galactic centers. Galaxies have different metallicities depending on their history. In astronomy, metals refers to any element heavier than hydrogen and helium. The more generations of stars a galaxy has gone through, the more metals it contains. Young galaxies, still forming their first stars, have low metallicity, mostly hydrogen and helium. Older galaxies, with many generations of stars, have higher metallicity, enriched by supernova explosions and stellar winds. By measuring a galaxy's metallicity, astronomers can learn about its history. How many stars has it formed? How quickly? Has it merged with other galaxies, mixing in their enriched gas? Metallicity is a chemical fingerprint, a record of stellar life and death, written in the composition of gas and stars. Every galaxy's metals tell a story of creation, destruction, and renewal. Some galaxies are invisible in visible light, but shine in radio. Certain galaxies emit very little visible light, but are bright sources of radio emission. These radio galaxies often harbor active supermassive black holes that produce powerful jets. The jets interact with the surrounding medium, creating enormous lobes of radio emission that dwarf the galaxy itself. From Earth, these lobes can span the sky, visible only to radio telescopes. The galaxy at the center may be faint or hidden by dust, but its presence is revealed by the energetic structures it creates. Radio galaxies remind us that light is just one way to see the universe. By observing in different wavelengths, we uncover layers of reality hidden from our eyes. Galaxies cluster together in superclusters. Galaxy clusters themselves cluster into even larger structures called superclusters. These are among the largest known structures in the universe, spanning hundreds of millions of light years. Our own Milky Way is part of the local group, which is part of the Virgo supercluster, which is part of an even larger structure called Laniakea. Superclusters are loosely bound, connected by filaments of dark matter and gas. They're not tightly packed like galaxy clusters, but they represent the largest organized structures that exist. Beyond superclusters, the universe becomes more uniform, the cosmic web of filaments and voids stretching as far as we can see. At this scale, the universe looks almost fractal, structure within structure, repeating at ever larger scales. Some galaxies have arms that trail like water behind a boat. In spiral galaxies, the arms often trail behind the direction of rotation, like ripples in water left by a moving boat. These trailing arms form because of density waves moving through the disk. The stars and gas aren't moving with the arms, they're moving through them. As they enter an arm, they slow down slightly, compressing and triggering star formation. Then they emerge on the other side, continuing their orbit. The arms themselves rotate more slowly than the stars, creating a persistent pattern. This mechanism, called density wave theory, explains why spiral arms are stable and long-lasting. They're not made of the same stars over time, but they maintain their shape. a wave of density moving through the galactic disk, like a frozen ripple in space. Galaxies can eject stars into intergalactic space. Sometimes, stars are flung out of their home galaxies, ejected by gravitational interactions or supernova explosions. These rogue stars drift through intergalactic space, alone and far from any galaxy. Some may have been ejected during galaxy mergers. Others might have been kicked out by close encounters with black holes. These stars can travel for billions of years, moving through the void between galaxies. They're hard to detect because they're faint and isolated, but surveys have found some. Imagine a star wandering alone through the darkness, far from any neighbors, no galaxy to call home, just drifting through the cosmic night. It's a lonely existence, but these stars are survivors, carrying their light into the emptiest regions of space. Some distant galaxies appear stretched like cosmic taffy. Gravitational lensing can stretch the images of distant galaxies into long, thin arcs. These arcs curve around massive foreground objects, distorted by the bending of light. Some are stretched so much they look like cosmic taffy, pulled and warped into surreal shapes. Despite the distortion, astronomers can study these galaxies in detail. The lensing magnifies them, making faint features visible that would otherwise be too dim to detect. By modeling the lensing effect, scientists can reconstruct what the galaxy actually looks like and learn about its structure, star formation, and evolution. These stretched galaxies are beautiful accidents. Their light twisted by gravity into forms that seem almost artistic. Galaxies can trigger each other's star formation. When two galaxies pass close to each other, their gravitational interaction can compress gas clouds in both galaxies, triggering waves of star formation. This is called tidally induced star formation. The galaxies don't have to collide. Just passing nearby is enough. The tidal forces stretch and squeeze the gas, creating regions of higher density where stars can form. Over time, this interaction can deplete the gas in both galaxies, eventually quenching star formation. But for a while, both galaxies light up with new stars, their disk glowing with the blue light of young, massive stars. These interactions are part of how galaxies evolve, shaped not just by their own internal processes, but by the presence and influence of their neighbors. The Milky Way is moving through space at 600 kilometers per second. Our galaxy isn't sitting still. It's moving through space at about 600 kilometers per second, pulled by the gravity of nearby structures. We're falling toward the Virgo cluster, and beyond that, toward an even larger structure. This motion is called peculiar velocity, the movement of a galaxy relative to the expansion of the universe. Despite this incredible speed, the motion is so smooth and constant that we don't feel it. Everything around us, the Earth, the Sun, the stars, is moving together. From our perspective, it seems like we're at rest, but in the cosmic reference frame, we're hurtling through space, carried by invisible currents of gravity that flow through the universe. Some galaxies have shells of stars from past mergers. When a small galaxy merges with a larger one, it doesn't always blend smoothly. Sometimes, its stars are scattered into shells, faint arcs that surround the larger galaxy. These shells are like ripples in a pond, expanding outward from where the merger occurred. They're made of stars from the smaller galaxy, now spread out in concentric layers. Over time, the shells fade as the stars disperse and mix with the larger galaxy. But for a few 100 million years, They remain visible, ghostly reminders of a galaxy that once existed independently. Shell galaxies are rare but striking, their layered structure revealing the violence hidden in what seems like a calm, settled system. Galaxies can be caught in gravitational tug-of-war. In dense environments like galaxy clusters, multiple galaxies can exert gravitational forces on a single galaxy simultaneously. This creates a tug-of-war, pulling the galaxy in different directions. The result can be dramatic, tearing streams of stars and gas away, distorting the galaxy's shape, and triggering bursts of star formation or quenching it entirely. These interactions shape the evolution of galaxies in clusters, making them different from isolated galaxies. They tend to be more elliptical, with less gas and less star formation. The cluster environment is harsh, and only the most resilient structures survive intact. The rest are transformed, stripped, and reshaped by the relentless pull of gravity from all sides. Some galaxies have cores that shine like quasars. A small number of nearby galaxies have active cores that resemble quasars but are less luminous. These safe-Earth galaxies have supermassive black holes that are actively feeding, but not as vigorously as in quasars. Their cores shine brightly in X-rays and ultraviolet light, powered by the infall of gas. The rest of the galaxy remains visible, unlike quasars where the core often outshines everything else. Safe-Earth galaxies give us a chance to study active galactic nuclei in detail, observing both the central engine and the surrounding galaxy. They're like miniature versions of the most energetic objects in the universe, allowing us to explore the connection between black holes and their host galaxies. Galaxies are moving away from us due to cosmic expansion. Nearly every galaxy we observe is moving away from us, and the farther away they are, the faster they're receding. This isn't because we're at the center of the universe. It's because the universe itself is expanding. Space is stretching, carrying galaxies along with it. From any galaxy's perspective, all other galaxies appear to be moving away. This expansion was discovered by Edwin Hubble in the 1920s and remains one of the most profound observations in astronomy. It tells us the universe had a beginning, that it's dynamic, not static, and that it's still growing. Every distant galaxy is a participant in this expansion, drifting away into the dark, carried by the stretching of space itself. Some galaxies produce superwinds that reshape their structure. In galaxies with intense star formation or active black holes, powerful winds can blow outward with tremendous force. These superwinds carry gas, dust, and energy away from the galaxy, sometimes at speeds exceeding 1,000 kilometers per second. They can sweep the galaxy clean of star-forming material, effectively shutting down future star formation. Superwinds also enrich the intergalactic medium with metals, dispersing the products of stellar evolution across space. They're a form of feedback where the galaxy regulates its own growth. Too much star formation generates winds that blow away the fuel, slowing things down. It's a self-regulating cycle, a balance between creation and destruction that shapes how galaxies evolve. The observable universe contains galaxies we'll never reach, because the universe is expanding and that expansion is accelerating. Some galaxies are moving away from us faster than light, not through space, but because the space between us is growing. Light from these galaxies can still reach us if they're within the observable universe, but we can never reach them, even if we traveled at the speed of light. Over time, more and more galaxies will slip beyond this cosmic horizon, disappearing from view forever. The observable universe is shrinking in a sense, not in size, but in the number of galaxies we'll ever be able to see or study. The cosmos is vast, but only a portion of it will ever be accessible to us. Some galaxies contain hypervelocity stars. In rare cases, stars can be ejected from galaxies at speeds exceeding 1,000 kilometers per second. These hypervelocity stars are thought to be flung out by close encounters with supermassive black holes. When a binary star system wanders too close to a black hole, one star can be captured while the other is ejected at incredible speed. These stars travel so fast they can escape the galaxy entirely, becoming intergalactic wanderers. Astronomers have found several hypervelocity stars in the Milky Way's halo, moving so quickly they'll eventually leave our galaxy and drift through the void. They're cosmic exiles, refugees from violent encounters, carrying their light into the loneliest regions of space. Galaxies sometimes form in unexpected places. Most galaxies form in regions where dark matter is densest, where gravity has pulled matter together over billions of years. But occasionally, galaxies are found in cosmic voids, the vast empty regions between filaments. These void galaxies are rare and puzzling. How did they form in such underdense regions? Some may have been ejected from denser areas by gravitational interactions. Others might represent unusual conditions in the early universe. Studying these galaxies helps astronomers understand the range of environments where galaxies can form and survive. The universe is full of exceptions, and every exception teaches us something new. Some distant galaxies are magnified by cosmic lenses. Gravitational lensing doesn't just distort galaxies, it magnifies them. Some distant galaxies appear much brighter than they would otherwise because a massive foreground object, like a galaxy cluster, acts as a lens. This natural magnification allows astronomers to study faint, distant galaxies in detail, observing features that would otherwise be invisible. In some cases, lensing magnifies a galaxy by factors of 10, 50, or even 100. This has allowed us to see some of the faintest and most distant galaxies ever observed. Objects that would be completely invisible without the lens. Gravitational lensing is a gift from nature, a cosmic telescope that helps us peer deeper into space and time than our instruments alone could reach. Galaxies hold clues to the nature of dark energy. Dark energy is the mysterious force accelerating the expansion of the universe. It makes up about 68% of the universe's total energy, but we don't know what it is. By studying how galaxies cluster, move, and evolve over time, astronomers hope to learn more about dark energy. Large surveys map millions of galaxies, measuring their distances and velocities. By analyzing this data, scientists can trace how the universe has expanded and how structure has grown. Galaxies are like test particles, tracing the influence of dark energy across cosmic history. In their motion and distribution, we may find answers to one of the deepest mysteries in physics. Some galaxies have been watched for decades. Astronomers have been observing certain galaxies for decades, tracking changes over time. They've watched supernovae explode, stars brighten and fade, and gas clouds collapse into new star-forming regions. Long-term observations reveal how galaxies change, even on human timescales. Though galaxies evolve over billions of years, some processes happen quickly enough to observe within a single lifetime. These observations help astronomers test theories, refine models, and understand the dynamic nature of galaxies. Every galaxy has a story, and by watching carefully, patiently, we can read a few pages of that story, frame by frame, year by year. And somewhere tonight, new stars are being born. Right now, in distant galaxies scattered across the universe, stars are forming. Gas clouds collapse, heat rises, and nuclear fusion ignites. New suns flicker into existence, lighting up their surroundings and beginning lives that may last millions or billions of years. This process is happening constantly, in galaxies near and far, a quiet, persistent act of creation. Each new star is the beginning, a chance for planets, for chemistry, for complexity. And in the vastness of the cosmos, those beginnings add up. Trillions of stars, trillions of stories, all unfolding simultaneously across space and time. The universe is not finished, it's still being made. And in that endless becoming, there's a kind of comfort. Life continues, light persists, and the universe, vast and ancient, still dreams of what might be. And now, with the final fact gently fading into silence, let yourself rest fully. We've traveled across billions of light years tonight. We've seen galaxies in every form, spirals and ellipticals, giants and dwarfs, galaxies colliding, merging, and being born. We've glimpsed the cosmic web, felt the pull of dark matter, and watched light stretch across the expanding universe. These distant galaxies are not just objects in space, they're moments in time. They're islands of light carrying stories from the beginning of the universe to the present day. And in their distant glow, we find something profound, a reminder that we are not separate from the cosmos. We are part of it, made of the same atoms, shaped by the same forces, drifting through the same dark. So wherever you are now, let your breathing slow. Let your thoughts soften and blur. Let the vastness of space cradle you gently. The galaxies will continue their slow dance through the void. The stars will keep shining. And you, here and now, can simply rest. If you'd like to explore more of the universe in this quiet, drifting way, consider subscribing. There are always more wonders to discover, more questions to ask, more journeys to take, one sleepy soul at a time. Sleep well. And thank you for traveling with us through the cosmos tonight. May your dreams be filled with starlight, and may you wake feeling as vast and peaceful as the universe itself. Good night.